this time we'll study the free fall model in which the air resistance is proportional to the square of the velocity. So this is the other model we're interested in as far as air resistance. And it makes some sense because when an object falls, it presents against the onrushing air, it presents an area. And the area is a second dimensional measurement, and so square of the velocity in a sense is related to area, you might think, at least as far as being second order. So there's some logic to making this assumption. And like I said earlier, the actual reality is somewhere, as I understand, is somewhere between first power and second power of velocity when it comes to air resistance. So anyway, let's proceed. Now, I think I set these up a little bit differently than your textbook. Your textbook leaves the mass off of here, and but let me explain why I'm doing it my way, and also again, where does this come from? So remember that Newton defines force as mass times acceleration. Second derivative is position as acceleration. So mass times acceleration. This is total force equals mass times gravitational acceleration is the force going downwards. And so that's the gravitational force going downwards. We can call it weight, the weight. And the opposing force in the opposite direction, that's why I've got it subtracted here, is mass times the second power of velocity. And to get the units right, we also need this constant of proportionality k. And so that we have ultimately the correct units are built into it. So we have force equals force minus force. Well, I like putting the mass here because this allows us to just cancel it off by division. So the mass really doesn't affect the free fall, at least in these models. So divide mass out, we have y double prime is equal to g minus k times y prime squared. So square of the velocity is represented there. Alrighty. As a matter of fact, actually mass does not affect free fall. But if you get into details, like when Galileo did his famous experiment of dropping cannonballs off the Leaning Tower of Pisa, he dropped two different sizes. And in fact, the larger cannonball did strike the ground just slightly ahead of the small cannonball. And it has greater mass. It also has, proportional to its mass, it has less area presenting it. And so it really didn't get cushioned as well coming down. That's why the bigger object fell slightly faster. At least I think that's what it is. But we to build that into these models would really greatly complicate it. So, but if you were to drop, say, two different masses in an airless environment like the moon, there's a famous experiment that one of the astronauts did on the moon. He had a feather and a hammer. He dropped them at the same time, and they fell at the same time. Wouldn't happen on Earth because the air would cause the feather to float, but in a vacuum they would just drop at the same time. Alright, well, let's get on to working this problem. And like before, I'm going to work this as a first order equation rather than second order, using the fact that y prime is velocity and y double prime is the derivative of velocity. So I can look at this as v prime equals to g minus k v squared. So there you have it. Now, this is kind of our basic equation we're going to solve. And this one's going to get pretty messy. And you'll see that as we start to proceed here. But remember, the v prime is derivative of velocity with respect to time. And velocity is a function of time. So there are two variables here, velocity v and time t. And if I multiply this equation by dt, and then also divide by g minus k v squared, then we're going to get dv over g minus k v squared is equal to dt. So in other words, I've managed to separate the variables, and with them all separate, we're able to now integrate both sides because we have differentials on both sides. So this one's going to be pretty messy. So I'm going to erase up here and start to work this one over. First thing I'm going to do is to take this denominator and factor it, and as a difference of two squares in a sense, and you can verify that if we multiply this together, these two conjugate expressions, then we'll get this expression here, the difference of two squares. So with that in mind, I can take this fraction and decompose it into two partial fractions. So this is the integration by partial fractions technique. And so here I need to figure out what numbers go up there in order to allow me to split this up. So if I were to multiply this whole equation by g minus kv squared, in order to clear the denominators, then we'll get 1 equals to a parentheses square root of g, and I've got a little mistake up here. Please correct that in your notes. That's a plus sign right there. So these have to be opposite signs. Alright, so square root of g minus, this will clear and we'll leave that factor left over. So I have square root of k times v plus, okay. And then plus over here, this term cancels, leaving this term times b times square root of g minus square root of k times v. There we go. And so I'm going to try to remember this integral here as I work out this partial fraction. At this point, I think I'm going to make a substitution here that will make this part equal to 0. And so if I let v be equal to the square root of g over the square root of k in this equation, then when I put the substitution over here, the square root of k's cancel, leaving square root of g minus square root of g, which is 0. So this term is 0 when I make the substitution. That gives me 1 equals to a parentheses square root of g plus square root of k, and then multiply here square root of g over square root of k. And a nice thing happens here. Those two square roots cancel, and I have square root of g plus square root of g, which is a times 2 square roots of g. So this tells us that a, divide here, a is equal to 1 divided by this term, 1 over 2 square roots of g. Alright, so I've solved for that constant. Now, in order to solve for b, I want to make a substitution here that will cause this to cancel out and be 0. And we can do that by letting v equal to now minus square root of g over square root of k. So when we make that substitution, get a equals to basically 0. As you can see, you plug this in, you'll see that the square root of k's cancel. I get square root of g minus square root of g, which is 0. So I have 0a plus b times square root of g minus square root of k times minus square root of g over square root of k. And again, the square root of k's cancel, and happily the negatives cancel, and I get square root of g plus square root of g. I have the same thing. This is b times 2 square roots of g. So b is equal to the same constant, 1 over 2 square roots of g. Alright, got all that down? Let's now go back to the integral, which I had down here a minute ago, and we'll go ahead and plug all this stuff in and finish that integration. So this was our original integration, which I had down here earlier, and then we split this up into partial fractions, and the two constants were 1 over 2 square roots of g. So I factored out these constants, split up this fraction, and here's our integral. And then of course on the right side we integrate dt, we get t plus a constant. Okay, so let's go ahead and integrate this thing, and I've got 1 over 2 square roots of g. And then here, these are both logarithms, aren't they? Because they have the du over u or dv over v form. And the first one is going to be the natural log of, what would this be? Actually, it's going to be, tell you what I'm going to do. I'm going to do this one first, because it's less complicated. It doesn't have this minus sign. So if you don't mind, I'm going to integrate this part first. And I believe we're going to get 1 over the square root of k times the natural log absolute value square root of g plus square root of k times v. And now that's just this part of the integration. Now let's check that, because if I take this derivative of the natural log, I get 1 over this term. And then the chain rule says I have to multiply by the derivative of this portion. This derivative would be 0 plus square root of k. And so to get that chain rule square root of k to cancel out, I need to divide by square root of k. So now that's correct. You can take this derivative and get back to that term. And then what's different over here, when I integrate this, I need a minus sign because of the negative. So this will be minus 1 over the square root of k. Hope my k's are legible. Let me rewrite that k there. Square root of k. There we go. And we have natural log absolute value square root of g minus the square root of k times v. Close that bracket. This equals to the right side, which was t plus the constant. Now then, let's do a little simplifying here. I can factor out the square root of 1 over the square root of k. So now I've got 1 over 2 square roots of gk. And the logarithm can be combined because we're subtracting these two logs. We can combine them together as a division, as a quotient. So I have natural log of, let's see, square root of g plus square root of k times v over square root of g minus square root of k times v. And this all equals to t plus the constant. So there we are so far. And now, have we forgot what we're going for? We want to solve for velocity. So we still have quite a bit of work to do in order to solve for velocity. And at this point, I'm going to simplify the issue a bit. And because I'm going to try to keep this model a little simpler. So here's what I want to do. I'm going to make the assumption that initial velocity is 0. In other words, we're going to work that free fall problem, jumping out of an airplane at 10,000 feet. When you just jump out, there's no initial velocity going down. So I'm going to make the assumption that the v of 0 is 0. In other words, initial velocity is 0. The reason I want to do, well, I want to do that in order to keep this model a little bit simpler. And but also, at this point, I want to put that in the problem so I can figure out what my constant is over here. And so let's go ahead and do that. So if we plug in the initial velocity of 0 down into here, I'm going to get 1 over 2 square roots of gk times natural log. And what do we have here? If I put zeros in for v's, this whole part's 0. I have the square root of g over the square root of g, which is 1. Natural log of 1 equals to 0, 0 for t, plus a constant, c. So my constant is this calculation, and the natural log of 1 is 0, so it doesn't matter what that stuff is. My constant is 0. So we've simplified that a bit by determining that if we start off with no initial velocity, then my constant is going to be 0. Now, if we want to build initial velocity into it, then it's going to get a bit more complicated, because then we'll have numbers here. We'll have a logarithm, and we'll have to calculate for c. So a little more complicated. All right, so I'm going to erase that c there. And here we are. Now I'm going to go ahead and multiply by this fraction in order to begin simplifying this. So I multiplied by this fraction, rewrote everything up here, and let's erase this. And again, we're trying to solve for velocity v. So my next step would be what? We want to get rid of that natural logarithm. And we do that by making both sides an exponent of e. And so that cancels those portions. And we no longer need the absolute value, as it turns out. Don't believe we do. Anyway, we have square root of g plus square root of k times v over square root of g minus the square root of k times v. It's equal to e to the 2 square roots of gk times t. Alright, so now we've got some algebra ahead of us to solve for v. And let me just give you a foreshadow at the result for v is going to be pretty interesting. It's going to be an interesting function. So hang with me here. I'm going to clear the fractions. Multiply both sides by square root of g minus square root of k v. That clears that fraction. So I have square root of g plus square root of k v is equal to, now I'm going to split these up. So this times this number here. So I have the square root of g e to the 2 square roots of gk times t minus square root of k times e to the 2 square roots of gk t times v. And that's a bit messy, isn't it? Now, we're trying to solve for v, so I need to get the v terms on one side. That means I'm going to add this to get it over to the left, and I'll subtract this to get it to the right. And so we have the square root of k times v plus this term, square root of k, times e to the 2 square roots of gkt times v equals to square root of g e to the 2 square roots of gkt minus this term minus square root of g. Alright, so that looks pretty messy, but one thing we can do here is to factor out the square root of k and factor out v. So I got the square root of k times, and I'm going to factor out v also, so that'll leave us a 1 in this part. 1 plus e to the 2 square roots of gk times t, and then times v. So we factor out square root of k and v. We're left with this term. Over here, let's factor out the square root of g. And that'll leave us e to the 2 square roots of gkt minus 1. Okay, now we want to solve for v. That means I need to divide by this piece right here, don't I? So let me erase everything down to here, and we'll do that. So I divided by square root of k, that's square root of g over square root of k right here. I divided by this term, but I switched the order of addition, and for a reason here, because this point I made a little error in taping this and had to come back to this point, so the editing may not be terribly smooth on this video, but at some point I think I explained where this came from. We solved for v, and here's where I'm going with this. There is a wonderful function that represents this in a very concise way, and it's a hyperbolic function. So what I want to do before we move on is to quickly review the hyperbolic functions. And one of them is called the sinh function, hyperbolic sine. And the sinh function is e to the x minus e to the negative minus x over 2. And then there's the cosh function, cosh, hyperbolic cosine or cosh, is e to the x plus e to the minus x over 2. And when I was videoing a minute ago, I had these reversed, and I just made a whole mess of it. So I had to start over on this explanation. Okay, you might wonder where these come from, so let me just digress a minute. And they seldom show up, but they show up in two places that I'm aware of. Of course, this is one place they show up. It turns out that I'm kind of giving it away, but this is a hyperbolic tangent function. And then when we solve for position, we'll get the cosh function will become involved. But the other place where these famously appear are in catenary curves. So if you take a loose cable or rope and dangle it between two level points, then it'll settle into a very natural shape, which is called the catenary curve. Catenary. And bridge builders thought that was pretty good, because the catenary takes a shape because all the forces are equally distributed on the cable. So if you want to build a bridge, one thing you could do is create a span which has a catenary shape and run these supports down to the roadway, and these supports all are bearing the same amount of weight. So in other words, the weight of the bridge is equally distributed along this catenary span with each of those struts. Very efficient way of building a bridge, very stable way of building one. So that's it's a catenary. Well, a catenary curve is basically a hyperbolic cosine, a cosh function. And so that's kind of a nice place. The St. Louis Arch, when the engineers designed it, the arch is a catenary curve. It's a hyperbolic cosine, turned upside down like this. And the idea is that all the weight of this 600-foot tall object is all equally distributed going down, so it's going to be a very stable structure. Alright, well, the other places, of course, show up are in this free fall problem. Do they show up anywhere else in engineering or physics? I don't know. Perhaps they do. But with this in mind, we'll go back to this problem, and here's my point. If we take the sinh and divide it by cosh, the analogy is sine over cosine. It's a hyperbolic tangent, or tanh. And when we divide these, we're canceling off the 2's, so we have e to the x minus e to the minus x over e to the x plus e to the minus x. So that's what this is in disguise. It's a tanh function. Okay, the other last thing is, if you're wondering, the H stands for hyperbolic. These hyperbolic functions are related to hyperbolas, and I forgot the exact relationship. It's some kind of area calculation that they're tied into. So there's a natural connection between these functions and hyperbolas, and you can look that up if you're interested. It is pretty interesting. I just don't remember it off the top of my head. Alright, so remember that this is the tanh function. Now, what am I going to do with that mess up there? I'm going to multiply top and bottom by e to the minus square root of gk times t. And when we do so, then we'll get the velocity function, square root of g over k, is equal to that mess. And when I multiply here, one of these cancels off, so I have e to the square root 1 times square root of gk times t minus e to the negative square root of gk times t, all divided by something rather similar, except there's a plus sign. There we go. So a minute ago I had the hyperbolic tangent function written down, and this is what this is. It's literally a hyperbolic tangent, or tanh. So I can now write the velocity function as a function of t is the square root of gk, g over k, times the hyperbolic tangent of, here's my input, it'll be square root of gk times t. And there we go. So there's the velocity all bundled up rather nicely into a tanh function, and you should have a hyperbolic tangent key on your calculator. I think on my calculator I've got to go to the catalog to find it, and so some calculators it's easier to get to, but yep, there it is. I have TANH on my calculator. So I'm going to store that into my custom menu here, and so I don't have to go back and find it. Oh, I already have it stored. Okay, so we're got that covered. Well, let's take stock of where we are. The free fall problem, we assume initial velocity was 0, and we solve for velocity. Now we also want to solve for position. So let me do some erasing and we'll work on the position function. I rewrote my velocity function up here, and now the position, y of t, would be the integral of the velocity with respect to time. So I've got to integrate this mess up here. And when I integrate, I'm going to factor out my constant. So I have the constant square root of g over k, and then integrate tanh of square root of g k times t dt. And what's the integral of tanh? Well, the integral of tanh, and you can look it up. Let me just do tanh of x dx. That's the integral of sinh over cosh dx. And if I did a little substitution here, let u be equal to cosh of x, then du is going to be the derivative of cosh. And the derivative of cosh, is very easy to verify that the derivative of cosh is positive sinh. So it varies a little bit from the trigonometry, because in trig the derivative of cosine is minus sine, but with hyperbolics it's going to stay positive. And so we end up with basically du over u. Du over u, which is a logarithm, natural log of u. And when I replace u, I've got the natural log of the cosh function. And then we would have a additive constant here, plus c. Alright, so basically the integral of tanh is natural log of cosh. Now you can look that up also. Some textbooks, calculus books have this in the back in integral tables. But it's not a hard integral to figure out, provided you remember a few things. Okay, so, and by the way, I don't need the absolute value because the cosh function, e to the x minus plus e to the minus x over 2, is always positive. And so this is always positive. I don't have to think about absolute values here. Well then, alright, so let's go ahead and integrate this. So I go to integrate this, I have this constant, and this would be a natural log of a cosh. I'm going to leave a space here for a constant here. So I have natural log of the cosh of this argument of the function, square root of gk times t. And when I take this derivative, the chain rule is going to give me a multiplication of square root of gk. So to get that to cancel, I have to multiply by 1 over the square root of gk. And so you can verify that if I ignore this part here. If I take this derivative, then I'm going to get a tanh function times the constant square root of gk. So I need that to cancel. Alright, so what's that give us? Well, that cancels the g's up here and gives me 1 over the square root of k squared, which is 1 over k. And by the way, sorry to give a little detail, we also still need that additive constant plus c. So when we clean this up, the position function is going to be 1 over k times natural log cosh parentheses square root of gk times t, and then plus a constant. And there we go. So we have velocity and position. So those functions, I'm going to go on and do that free fall problem out of the airplane.